Okay, so thanks a lot for the invitation to celebrate Jean-Pierre's memory. And I have many fantastic memories of Jean-Pierre. So I was here as a postdoc a few years ago, let's say. And I think it was a fantastic time. I think me and my family had some of our best years of our life. I think it was really great. So it's a great honor to be able to speak here. Okay, so maybe I will just first tell you something about this image. So it's a metaphoric image. It's not, strictly speaking, it's not me. And the landscape is not the mountains, because it's an image. You should think of that as the world of arithmetic geometry, or more specifically Arakelov geometry, and I'm a tourist in that world. You should really know that it's not really I happen to somehow get into that world and discover this beautiful landscape, so I'm going to report back as a tourist what I've seen, basically. So it's not really my expert domain, I have to say. But it's a beautiful world. Okay, so I will spend a lot of time, I guess, on just background and motivations, because I do realize that you are also, I guess, most of you tourists in this world. So let me start by explaining the notion of a height of a point. So it's a very simple concept. So we consider now a point on P1, but with rational coefficients, so to speak, so a rational point. And then the naive height of that point is just the following thing. You just represent this point by making sure that the greatest common denominator of xi is just 1. And then the naive height is just the logarithm of the maximum absolute values. Okay. But you should really think of that as a measure of the arithmetic complexity of that point, because, think of the simplest case. So we take the first coordinate to be 1, so then we just have a rational number, 1 over 2, so no common denominators. Okay, so it's the logarithm of 2. And you do the same thing for this number, which sort of, if you think of the real line, is very close to 1/2, but the height is quite large. Okay, and so what's the difference? Well, the difference is that this number has larger arithmetic complexity just in terms of information. You need more information to even store that in a computer, because there are more digits, right? So this is a measure of some arithmetic information in that number. Okay, so likewise, you go to higher dimensions. It's essentially the same thing. You make sure that the greatest common denominator is 1, and then you just take the logarithm of the maximum absolute value. Okay, so you should really think of this as there being sort of two ingredients. One is the arithmetic structure, which comes in here when you clear the denominators and nominators, and then the metric structure, which is the absolute value. And they are sort of appear here together. Okay, so now let me introduce metrics. So now, this naive height, there's a hidden sort of metric because it's an absolute value, so that's some kind of metric. But we can be more general. So we fix now a metric on the hyperplane line bundle on Pn. So that corresponds concretely to just one homogeneous function on Cn plus 1. For example, a complex norm. That will give you a metric on the one line bundle. And then we can do exactly the same thing. We clear nominators and denominators, and then I take the logarithm of the sort of norm of x with respect to this metric. So the naive height you get back by taking what is called in arithmetic geometry the Weil metric, which is just the L infinity norm here on Cn plus 1. Okay, so now your height depends on a metric, so you choose some metric, but it doesn't really make a huge difference, because if you compare, for example, with the naive height, they just differ by some overall additive constant. Okay, by some compactness argument. Okay, so what's the motivation for this notion? Well, so now the motivation comes from arithmetic problems. So let now x be a non-singular projective curve over Q. So concretely what that means is that we can embed x in some projective space, and in such a way that x is cut out by homogeneous polynomials with coefficients in Q. And then we look for rational points on X. So this is a time-honored problem, which goes back to the Greeks, I guess. We wonder, for example, how many rational points are there on this curve? Are there finitely many, infinitely many, and so on? And then the Mordell conjecture states that if you assume that the canonical line bundle of X is positive, so you can think of this as just you look at the canonical line bundle of the complex curve corresponding to this rational, this equation, you assume that that is positive, that is, say, ample, then the Mordell conjecture is that there are just a finite number of rational points. So and this is it's not a conjecture anymore because it was proven by Faltings in the 80s. And that proof actually uses height in a sort of non-obvious way, but it uses heights. So that's one motivation for using height. It gives you more control on the points by measuring their size in some sense. But of course, the proof is a lot more complicated than that, actually, obviously. Okay, but a good example to keep in mind that I will come back to is the diagonal case. So now I take an integer m, which is at least 4, and I look at this diagonal curve in P2. Here, so it's a Fermat curve. It's a generalized Fermat curve because I'm allowing these coefficients here. So the Fermat case is when you have 1, 1, minus 1. So a consequence of this proof of the Mordell conjecture is that there are only finitely many rational solutions to that equation. And famously, for the Fermat case, they are just trivial ones. But in general, all we can say is that they're just finitely many. Okay, but then there is still an open problem, which is the effective version of the Mordell conjecture. Well, I guess it's supposed more or less open, I guess. And the question then is, we can not only say that there are finitely many points, but actually bound effectively, in some explicit manner, the height of those points. So the naive height would be that you just can write down a very large number, 10 to the 7, or whatever, and say that the height of the largest point is no bigger than that. And that would be a really strong thing, because if you had that in principle, that means that you actually have an algorithm to find all the points. Because if you have a bound, if it's less than, say, 10,000, then, you can search through all these points on P2, which are just finitely many, and you can just, it's a very slow algorithm, but you could, in principle, just check which one lie on this curve. So theoretically, that would be quite amazing. Okay, but this way of formulating it's a bit naive, actually, because I'm hiding some things here. Because when I say that the height is bounded, first of all, x over q is just a scheme over q, strictly speaking, which has the structure of a scheme over q, projective scheme over q. And we need to pick an embedding to even define the height. And we also need to pick a metric on the OR1 line bundles. So we need these two things to even talk about the height, the embedding and the metric. So which one, when I say that there's an effective bound, for which embedding and for which metric you can ask. Right, so then I need to tell you something about models over Z when discussing embeddings, because an embedding, once you have fixed your embedding, that actually induces a model of your variety over the integers, by definition of a model, more or less. So what I mean is that once we have embedded X in some projective space, so we have some, say it's cut out by, so it's curve cut out by, say, one polynomial with integer rational coefficients, then we can get the integer coefficients. It's the same solutions. You just clear the denominators and nominators, and now I have integer coefficients. But that way of proceeding actually depends on the embedding. So in scheme theoretic terms, this will give you a scheme over a projective scheme over Z. And the way to, I guess most of you know what I'm talking about, and if you don't know, you probably won't learn it here. But the picture, there's a picture you can have in mind, which I think is very helpful. So once we have these, it's cut out by some polynomial with integer coefficients, say. So in scheme theoretic terms, that actually gives us a whole family of curves. Not only, I mean, we started with a curve over Q, I embed it, I have integer coefficients, and that will actually give me a whole family of curves. Because I can also look at, for a fixed prime number, say 2, I can look at the curve where I mod out 2 from the coefficients. This will now be a curve over the field with 2 elements, Z modulo ZP2. So I do the same thing for all the primes. So I have a family of curves now over field, the field FP with P elements. And the way geometrically think about it is that the original curve, x over q, is the generic fiber, because if this is, I mean, the base here is the spectrum of the integers, where you have 0 is the generic point, and then these are the closed points. So you've somehow just filled in the generic fiber by picking the model, as we do in complex geometry often as well. Okay, so what I'm saying is that once we fix the embedding, that will give me a model over Z, and that will give me some fibration of curves in this way. Okay, so that's what a model is. But the model also induces a line bundle on this scheme, because I have an O of line bundle on projective space, and then by restriction, as usual, that will give me a model for the line bundle, which I call this calligraphic L. Here. Okay, and then, okay, so this, I have a model, and if I just pick abstractly some metric on the complexification, so the complexification of the variety is just a complex variety, and now I complexify the line bundle, I have a complex line bundle over my complex variety, so I can fix a metric on that line bundle, and I can define a height with respect to that metric by imitating what we did concretely. So the way to do it is that you actually go to the dual of that line bundle over x. I look at the complex line over that x here, and it will have, I mean, a whole line of complex points, but I can choose, I mean, some of them will be defined over the integers, a lattice inside that complex line. So I pick a sort of the generator for that lattice, Sx, and I just take the norm of Sx. So let's actually pause there, because this is a bit shocking if you're doing complex geometry, because we always, I guess, tell our students that the metric, you have a metric on a line bundle, it's not really a function. It's sort of a local function, but it doesn't give us a global function, right? I guess we usually, that's what you would say in a course. And here I'm telling you that from the metric I get the global function, which is this logarithm of this thing. It's actually an enormous function. And the reason is that I'm using the arithmetic structure. And the price we pay is that it's certainly not continuous in any way. I mean, it was a huge jump between half and just something which is close to 1/2, as you saw in my example. But it's a global function, at least.
What's the star?
The star is that I go to the dual of the line bundle when I do this. It's so this star? Yeah, so it's not, I lift x I think of x and I look at the total space of the dual of L. That's a dual line bundle. It's just to get the, otherwise I would have to have a minus sign here, but it's not a big deal. Really. Yeah.
So, you say embedding uses the model carry x for x over z, but even the model itself could be different for a fixed embedding, right?
Well, I mean, for a nice, I mean, no, given an embedding, I take the risky closure of the generic fiber. That's the model. Okay. Yeah. In scheme theoretic terms. Yeah. Okay. Okay, so now let me state the effective Mordell conjecture in the form that it was stated by Parshin in the sort of late 70s, I guess, something like that. Okay, so let x be a non-singular projective curve over Q, and we assume that Kx is positive. And I said there are many ways of obtaining a model. Or millions of ways of embedding this curve in large projective spaces, right? But there's only one which is the best way, and that's called the stable model. So I'm not going into the definition, but basically it's a very simple definition in geometric terms. It's just the ones where this family of curves is as nice as you can imagine. So that's when they are all nodal curves, basically. That's more or less the definition of a stable model. Okay, so it's the best sort of model in some way. Okay, so the effective model conjecture is that if you pick this model and also a very special metric, which is called the Arakelov metric. So I'm not going into definition, but it's canonical, and it's the best metric with respect to the behavior when you do adjunction, basically. But it has some good properties that you want to use. Okay, so there is such a canonical metric. And then the effective model conjecture would be that this thing is bounded by some explicit constant c, which ideally would just depend on the degree of kx, or at least only on xq. I mean, I don't think it's clear what really to expect here, but I mean, it's a free world. You can hope for whatever. I mean, as long as there is no counterexample, you can hope for the best, I guess. Okay, so that's the sort of effective model conjecture people have looked at. And then Parshin posed a question, which is really an approach to prove this. So the thing is, so what do we want to do? We want to estimate the height of the points on X. But we have to do this for every point, and we don't even know if there are, so we would have to have this uniform bound for all the points. And the idea of Parshin is to say that, well, there is actually, using, I'll come back to that Arakelov geometry, you can talk about the height of the variety itself, or the model with respect to this metrized line bundle. And he said, let's first try to estimate that. So I will give you soon. I will give you a definition. Let me just give you the intuitive way to picture the height of X with respect to the line bundle. So the way to think about it, it will be a top intersection number, morally, because as I told you, we have this fibration over spec Z, which you think of the affine line over Z. Okay, so we have that fibration, and then you'd say, okay, so let's look to get an invariant of that thing. It's a surface, so we could try to just write down, and we have a line bundle on that surface. So let's look at the top intersection number, which is L intersected with L. Yeah. Okay, but that doesn't even work in complex geometry in this picture, right? Because it's not a compact space. So the base is not even compact. So the total space, it's an affine line. The total space is not compact, and we cannot define intersection numbers. There's no well-defined notion of intersection numbers. You have to add some structure at infinity, which in complex geometry is a compactification. You have to fix that compactification. And here, unfortunately, it doesn't make sense to compactify spec Z in any reasonable way or in any classical way. But it turns out that the metric plays the role of a compactification. So that was this beautiful idea of Arakelov, that the metric is your replacement for a compactification in this landscape. And it sounds a bit outlandish, but it's really natural if you really compare Archimedean and non-Archimedean geometry and so forth, but I'm not going into that. So what I'm saying is that we can define this intersection number if we allow it to depend on the choice of metric, because that's the analog of a choice of a compactification. Okay, so there is such a thing. I'll give you the definition later on. So Parshin's question, it seems that he doesn't want to call it a conjecture, is the following, is that the question is, can you bound the height then of this stable model with respect to Arakelov metric divided by the degree in this universal way? So it should only depend on first the coefficient here, A0, a number A0, only depending on Kx. And then it has to depend in some weak way on the model. because it will depend on the number of bad fibers here, because in this analogy, you have some of these fibers will be non-smooth. I mean, it will be a non-smooth morphism, this projection. And for some p, when we do this, look at the scheme over fp, it might be singular. Then we call that prime bad, and then we just add the logarithm of those p's with a coefficient. So this is Parshin's question, and the reason he asked it because he would be very happy if the answer was yes, I guess, because that would actually imply the effective Morel conjecture. With the caveat, though. So let me tell you something about the caveat. The caveat is, I mean, ideally you would say that, okay, I start with my x, I want to estimate the height of its points, so maybe it's enough to estimate the height, not of the points, but of the model itself. That doesn't work, unfortunately. It's not the height. You need this universal bound for all models in some sense, and all varieties with kx positive. Because in the argument, what you do is that to control a given point, actually look at a ramified cover of your curve, which is ramified exactly at that point, and the height is basically the height of that curve instead. So you will have a whole, I mean, since there are many points, you need to control the height of many curves, actually. But the goal then is that if you could prove this universal bound, that would be enough, basically. Okay, so why? Okay, I mean, it's a free world. Again, you can pose any conjecture you want, but it's really guided by this analogy with the complex geometry picture, because it's really inspired by the Miyaoka inequality for complex surfaces. So, I mean, very briefly, the idea is that if you would instead have a complex surface, you would try to write down the same thing, and you look at the stable model, then there is the analog inequality does hold in that case, which was shown by Parshin, and there's a nice proof by Vojta and other people. And that follows from the Miyaoka inequality of that surface. So unfortunately, that has not been generalized. The proof seems hard to generalize to the integers. But so the question remains. And I do not obviously solve it here. So I will just, so this is just motivation for what the problem we looked at. Okay, so before stating something which is at least slightly related to this, the result, I'll give you the definition of a height of a model very concretely. So you do the following thing. So let's look at this general situation. I have a projective variety over Q of dimension n, and I fix a model over the integers, a projective model, and so forth. And I look at a line bundle which is relatively ample, so ample on all these fibers, basically, and it has a metric over the complexification. Then you can actually, I mean, there is an intersection type theoretic definition of the height, but you could take the following as the definition, which is the sort of Hilbert-Samuel type definition. So what you do is just the following thing, as usually for Hilbert-Samuel thing, and actually, yeah. So So what you do is that you take. So I look at high powers of my. So I have a scheme over Z. I can look at high powers of this line bundle. So if you're not used to schemes, you'd like to have some idea what this really is. But it's a very concrete thing, even if you're not used to schemes, because these are basically, once we've embedded X in a projective space, these sections are just basically restrictions of polynomials with integer coefficients. That's your sections which are defined over Z, these ones. So that is a Z module, even a lattice inside the space of all holomorphic complex sections. So it sits there. And that means that there is a privileged basis in the space of holomorphic sections, because you can demand that you pick a basis of these integer sections. So it really generates the integer lattice. So we do that, and then we form this Gram-Schmidt determinant, which is that I've also fixed the metric, and then I also fix the volume form. And that will give me an L2 product, or Hermitian product, on this vector space. So I form just this Gram determinant in terms of this integral basis. I take the determinant of that, the logarithm, and you go to the limit in this way. This limit exists. It gives you a number. And that's the height of this model with respect to the line bundle and the metric. And okay, so let me pause because this looks very similar to something we do in complex geometry and Kähler geometry. So let me just stress that, I mean, we made a choice. It's not allowed for it to depend on that choice. So where's that choice? We pick the basis. It define over Z. Okay, but what if I would pick another basis? Well, the absolute value of the determinant will, even the determinant, will not change, because when you compare determinants, you get the determinant of the change of basis matrix. That matrix has now coefficients in Z, and it's invertible, so the determinant is 1, basically. So that's why it's independent of the basis. And then we have made another choice. We picked this volume form, but that does not play a role in the limit when k tends to infinity. It's sort of washed out in that limit. So then, okay, so people doing Kähler geometry will recognize, but this is just Donaldson's L functional, actually. Well, but Donaldson's L functional, in that usually you have to pick this basis, and we usually pick it to be orthonormal with respect to some reference metric, which is another metric, which is just a reference metric. So that Donaldson, the limit then will depend on that reference, and we know the formula for the limit, but it depends on the reference. And here it is the arithmetic structure which plays the role of the reference instead, basically. Okay. Okay, I will actually skip that, so I will go directly to our main result. Well, it's actually we're writing a paper which hopefully will appear anytime. So this is one of the results, but there are a number of other results actually, but I will focus on this result. So this is joint work with my student Rolf Andreasson from Göteborg. So now we consider first the Fermat case here. Okay, so then we get this sort of explicit estimate that Parshin asked for, but in this very particular case. So I'll give you the number. Remember, this should be an A0 leading coefficient here and another coefficient here. So this one is, the important thing is that it's negative. And the other one is quite small here. So let's try, so what does that really mean? And it's actually quite tight somehow, because it's known that this intersection number in this case is always positive. And m is greater than 4. So here we have something negative. But because we take logarithm of m, it's a natural logarithm, it's indeed positive. So it's not a counterexample to the lower bound. That would be cool, but no. But it's a quite tight bound, I think. And it turns out that what is interesting is that it's negative, because if you really go deeper into this geometric analogy, in the complex case, it's a negative thing you would hope to get, actually. So that's nice, I think. And then actually, more generally, if you look at this sort of generalized Fermat curve, we have these integer coefficients, then you just have to add one positive term, which depends on the logarithm of these coefficients here. So I should say there were some previous bounds by Kuhn-Kurila in Arakelov geometry, but then these were not explicit as far as I understand. And there are some explicit bounds, but then they are polynomial in M by Javan-Pekar. But his results apply to more general Galois covers. And we actually use a Galois cover in our proof that I will mention later. So our result, I think, actually holds more generally as well. Okay, so let me tell you a little bit about the proof. And you wonder, of course, where did this minus 0.88 come from? It's probably the first time I write down a number which is not a formula, in a formula where there is it's not a sort of an integer, I guess. Yeah. So, okay, so the proof uses something we call canonical height. So to explain that, let's look at this general situation. I have a projective scheme over Z. So again, just some polynomial with integer coefficients cutting out something. And I assume that the relative canonical line bundle is ample. And the complex, I can look at the corresponding complex variety, the complex points, and I assume that those are non-singular. Okay, so the basic case to have in mind is just the usual thing. We look at the hypersurface in Pn plus 1, which is cut out by a polynomial with integer coefficients and degree m, and then kx relatively ample just means that m is sufficiently large, as usual. So it's the usual adjunction formula which applies over the integers as well. Okay, so in that case, the canonical height is what it's natural for somebody with a background in Kähler geometry is the height with respect to the Kähler-Einstein metric, because we have to choose a metric. And in Parshin's inequality, it's the Arakelov metric. But if you do Kähler geometry, it's more natural, I think, to take the Kähler-Einstein metric, which we know exists. But there's one important thing. The Kähler-Einstein metric is strictly speaking not unique because, for example, in the Ricci, it says that the Ricci curvature is constant. But what is that constant? How do you choose that constant? There are different ways. But the point is that when you metrize the canonical line bundle, you're supposed to use the volume form of the Kähler-Einstein metric. So what we do is that we just make sure that we pick the volume form, which is normalized to have unit volume. That's the metric. It's important because the height will depend on scalings. So we really have to fix the scaling. Otherwise, it doesn't. I mean, we just want to get the number out. We're not allowed to scale because that would change that number. So this is the canonical scaling, so to speak, we use. Okay, so that's the canonical height. And the reason we work with that is that we can get something which is better than an inequality. We get an equality, a formula for that height. It looks a little bit complicated, so I'm just give you the most important ingredients in that formula. So this normalized height with respect to the normalized Kähler-Einstein metric has this structure. First, there is this first number, which is that you take 1 minus 1 over m, that's a number w, and you plug it into a transcendental function. So what is that transcendental function, which is a real analytic function of w? It has a sort of a complicated structure, but let me just tell you what's the most important ingredient. It's in the transcendental piece it involves is the Hurwitz zeta function. So the Hurwitz zeta function with respect to a parameter s and x is just this following generalization of the Riemann zeta function. So here's this x dependence. And it's well defined for s sufficiently large. Then you do analytic continuation. It becomes a meromorphic function of s. And you can set, it's allowed, we can set s to be minus 1 as long as x is strictly between 0 and 1, which it will be. So now I will always set s to minus 1. So now it only depends on x. And this x will depend on m in this complicated formula. But it's not only one value. I mean, several values comes in. But I mean, the important thing you have to remember is that it involves the Riemann, the Hurwitz zeta function at minus 1, and its derivative at minus 1. Okay, so this is the formula, and then the rest are just the log m coming from here, and the rest, this is 0 if we are in the Fermat case, which is the most important case. Okay, so this is an explicit formula. I'll tell you something about the proof later. Okay, so the thing is that once we have this equality for the Kähler-Einstein metric, that actually implies the inequality for the Arakelov metric, because first of all, I wrote down something which is sort of uniform in M. I have to control the M dependence, and that we can do with respect to some convexity argument. This is a very handy thing with the Kähler-Einstein metric. It satisfies some variational principle that will give you some convexity property. And then we need to compare what happens if you change the Kähler-Einstein metric and replace it with the Arakelov metric. That difference is some analytic object, actually. And it has already been estimated in previous work by Jorgensen and Kramer. So we use that formula, and then we get the estimate I wrote down, basically. Yeah. OK, but then there's something very intriguing going on. So this is not related to Parshin's inequality, but I would show it because it's so intriguing. And maybe we have, we do have some number theorists. They know this much better than me. Maybe they can answer why this is what's going on here. So we made a very intriguing observation, is that when you look at Fermat curves of low degree, these degrees, so for some reason, I will tell you, not 8, it seems. 8 is an exception, it seems, here. For that reason, we get a more beautiful formula in that case. Because if you remember, the formula was sort of ugly. It's a Hurwitz, some combination of Hurwitz function and its derivatives. And it's sort of not so, sort of ugly in some sense. But I'm telling you that for these few degrees, it becomes a very more structured formula, because we don't see the Hurwitz zeta function appear, but it's a Dedekind zeta function, which is really a number theoretic object. So, just so let me just say, first of all, that it depends on some number field, so some finite extension of Q. That field will depend on M, so the field, what we have here depends on M, and what it is just here, it's just what you do the extension where you add to the rationals, you add a 2mth root of unity. It's basically the real part of the 2mth root of unity. Then you get the number field, which depends on M. And this is what shows up here, and it has a Dedekind function. Let me just say that it's sort of a generating function for the ideals in the ring of integers of that number field. But it's a different thing than the Hurwitz function. Certainly different. It's a number theoretic object. And then we also have something here, and it's just we get some explicit rational numbers here, and all the p's that show up in the formula are just the p's dividing M. So it's very structured formula compared to this other formula. And then what is intriguing is that, so why doesn't it not hold for A? And so I have we haven't proven that it's false for M equal to 8, but you can actually just do some numerics. If you believe, let's check by numerically if it seems that it can actually hold. So we did some numerics, and we plugged in Q. So if the only data here is because for M equal to 8, it's only log 2 that is relevant. So you can just check. You can plug in as large Q's rational numbers you can and see if it holds. And we checked up to 30,000, I think, the height being the height of that number, naive height being 30,000, and it doesn't hold for those, at least it seems. So that's a bit intriguing. And then you say, how would you ever? How come? Why does it hold for these numbers? And the reason is that it turns out that there are some connections to Shimura curves, and for Shimura curves, these curves, including actually M equal to 8, I think, for these curves, Fermat curves, they are related up to taking finite covers with Shimura curves. For Shimura curves, one expects to get something like this by basically something called the Kudla program, and Yuan has actually recently proven such formulas for Shimura curves. So that's why we expected this to be true, but it's just an inspiration, actually. We did not use that connection It's just an inspiration so you know what you look for, because you have some explicit formula and you need to sort of play with it, and it's hopeless if you don't know what you're aiming at, basically. But if you know what you're aiming at, it's not so hard, basically. But it's still intriguing why 8 is different, seems. Okay, so let me say something about the proof. Yes. Okay, so let me remind you. First I stated some inequality for the Arakelov metric, then I got an equality implying this inequality. For the Kähler-Einstein metric, I call that the canonical height. And I said we could prove a formula for the canonical height. So why is that? The reason is that the canonical height, for the canonical height, even if by definition it's the height with respect to a certain metric, the Kähler-Einstein metric, we can prove that that has a limit formula not involving a Kähler-Einstein metric, only algebraic data. So that's why it's more workable. And here's the structure of that formula. So one can prove then, we prove that the canonical height is just, you get by computing this integral, it's a limit, so you have to look at the nth powers of your curve x or over c, or your variety over c, and you have to integrate a very specific canonical algebraic top form, holomorphic or multi-valued holomorphic top form, which is canonically attached to x. So what is this holomorphic top form? Well, I do a similar thing as before. I look at but now I look at high powers of kx, and then I'm going to write down a very special holomorphic section on this product and take the kth root. So what is that section? It's, as before, I form a determinant, but now I don't take any scalar products. I just think of the determinant as a holomorphic section on x to the n, defined in terms of the z basis. Okay, so that will give me a holomorphic section on this product with values in the, oh, there is a missing, yeah, with this guy has values in the kth tensor power of the canonical line bundle of that product. But if we take the kth root, that's actually a multi-valued holomorphic top form on that product, which is this alpha n. And when you wait, this thing will actually be an honest measure that we can integrate. And again, it will not depend on the choice of basis. So the magic is that the height is actually just this limit where you don't see any metric appearing. Okay, so that's very useful. And the proof of that actually uses the probabilistic approach to Kähler-Einstein metrics that I've played with a lot for the last years. So this is a sort of an arithmetic application of that. Yeah, I just won't say anything more about that. But the important thing is on the right-hand side, we're basically computing a period, actually. It's an integral of a holomorphic top form, basically. Okay, so that's back now to the Fermat case, why this is useful. Because we can compute this integral explicitly. That's why it's useful. So, okay, so we have a Fermat curve, and then it's useful to think of that curve as being branched over P1 there's a standard way. You just find a finite map to P1, which is branched at 0, 1, and infinity. And that means that when we compute, I said we just have to, in this case, this formula I wrote down, you can just check what it becomes when you express it on P1 instead of on the curve. And then you just have to do this integral here. Okay, so it's a very explicit integral. How hard can it be? How hard can it be? And if you know your special function, it looks very much like a beta function, actually, or the gamma function in several variables. And luckily, physicists had already computed this formula. So you just, turns out, and it has, it's related to some Selberg integrals in number theory. And it appears in work on conformal field theory. And there's an explicit formula for this integral, and it's a product of of gamma functions, factors. Gamma functions shifted by in some way. So when you take the logarithm, it's a sum of logarithms of gamma functions. And in the limit, you get an integral of that. Here's the integral. And then you look in your handbook on special functions. And that integral is basically a primitive of the Hurwitz zeta function. So this is why, in the end, we get a formula involving the Hurwitz zeta function. Yeah, I think that's all I had to say. Thanks.